All right, welcome to the presentation Interactive Geo-Information in Virtual Reality, Observations and Future Challenges. My name is Juho-Pekka Virtanen. I come from Aalto-Yliopisto School of Engineering and currently work there as a postdoctoral researcher. Within Aalto, we have a unit called Research Institute of Measuring and Modeling for the Built Environment. We are a joint institute between Aalto University and the Finnish Geospatial Research Institute, focusing on multidisciplinary three-dimensional applications within the built environment. I will start this presentation by discussing game engines, geoinformation, and virtual reality briefly. I begin this by discussing game engines as they are absolutely essential for developing VR applications. The vast majority of current VR applications are built on commercial game engines, such as Unity or Unreal Engine. In addition to this, they offer several other visualization modalities like augmented reality and have been applied for interactive 3D visualization in geoinformation for a long time before we had commercial virtual reality systems. So this blends into the research tradition of visualization in geoinformation and interactive 3D visualization. A major issue in using game engines for geoinformation applications is that the current commercial game engines do not readily support the multitude of data formats and types that are encountered in the geoinformation domain, especially if we go towards semantic, heavily structured models such as CityGML. This is a simplification, but we could say that to use these rich geoinformation assets in interactive 3D applications in game engines, everything has to be squeezed through the format of textured meshes. This is a side note, but it has to be added that the interest towards solving this issue doesn't only come from the geoinformation side, but there is also strong interest in the games industry towards the geoinformation discipline. So, for example, game industry requires more and more complex three-dimensional scenes, and cost for producing these is massive. So suddenly photogrammetry is something hip and cool if it helps us in building game engine content. In addition, several applications require GIS data in game engine, and this has been one of the motivations for developing libraries for easily including GIS assets in game engines. In this topic of geoinformation and game engines, there's a number of common misconceptions that are occasionally found from papers. First of them is that a textured model would be a complete game engine scene, usable for a variety of applications. The second is that after we have a model of an object or environment, any applications could be made with ease. And finally, the performance discussion is often reduced into discussion on polygon counts. After these more general thoughts, I'll move on to presenting some of our experiments in a very brief format. These experiments come from a project where the intent was to build a virtual reality application using indoor mapping and a variety of other data sources. The theme of the application is climate change and sustainable energy production. And in this application, we use not only indoor mapping, but also, for example, urban 3D model from airborne laser scanning and a number of manually modeled 3D assets in Unreal Engine. And the same application is deployed to two different virtual reality systems. So we are using both Windows Mixed Reality and the HTC Vive. For indoor mapping, we utilize the Matterport system. It's a commercial system with cloud-based processing that automatically produces textured mesh models from interiors. In this case, we have a multi-room interior, and as we wanted a model with doors between the spaces closed, each of the rooms was individually mapped. And to optimize the model for game engine use a bit, we apply some decimation, so we try to reduce the polygons from the mesh from areas where the variations in geometry are very small, so in practice where the surface is planar. In addition to the interior model, we used a segment of an urban model. This is based on airborne laser scanning with a fairly conventional modeling pipeline in TerraScan, where we produce a separate mesh for the ground surface and separate mesh for the building objects. For the ground surface, we apply normal mapping, so the mesh is significantly simplified, and then a normal map is generated to allow rendering in more detail whilst maintaining a low polygon count. This is a common optimization procedure in game engine content production, and here it is implemented in Blender. After all the assets are complete, there is of course the process of assembling the game engine scene by, for example, setting up objects for collisions and physics and limits for teleporting in virtual reality. So on the left-hand side, you'll see the mesh that goes for rendering, and on the right-hand side, you'll see the simplified objects that are used by the physics engine in this case. Next, I will show a brief video of the application in action, and this is shot through the VR headset, so this is a bit shaky, so try bear with me. Okay, so once we get going, we can start moving about in the environment and interacting with objects. Some of them are attached to a physics engine, so they respond realistically. We can move both by walking or teleporting. And in the modeled interior, there are several additional presentation data. These all relate to climate change and CO2 concentrations. This is due to the theme of the application. And they are implemented as video textures on mesh objects. Let's stop that. We are trying to build an environment that would respond to the user. Here you also see the urban model. It's actually quite interesting to look at them as huge scale models in virtual reality. And as I said, the application responds to the user, so you can, for example, switch the lights on and off in individual rooms, and the lighting will respond. And we also bring some animated 3D models into the scene. These all relate to the theme of the application. It's a bit tricky to navigate in dark. And because we are using real-time lighting in Game Engine, we can also implement things such as a virtual flashlight. So here you see the user navigating in torchlight. And of course, these objects also respond to the physics modeling. So if I drop the torch, it will actually land on the floor. There. Okay, and then let's get the glasses off. All right, now that we have an overview of the application and its functionalities, what are the observations that we made whilst producing this? Firstly, about the performance. This graph depicts the frames per second rendering attained using this application on 2 different virtual reality systems and 2 different rendering resolutions. And basically we add 1 real-time light to the scene every 30 seconds. And from this we can see that even on the same system and exactly the same scene, a very different performance is reached due to different rendering resolution. And of course, the amount of GPU power available on the system has a big impact on the performance. So if we have a high performance desktop computer, we can run close to 90 frames per second, but on a more limited gaming laptop, we fall close to 50 frames per second. And even on a very powerful system and a very sort of a considerate polygon count in the model, we can completely destroy the performance by making the rendering otherwise too heavy. So for example, by adding too many real-time lights, and finally the engine is not able to maintain a sufficient performance. And these frame per second counts are already way too low for comfortable use in VR. Secondly, about the game engine scene. So even though we had an automatically produced mesh model of the interior, to make it usable as a game engine scene, we had to do a number of manual steps, such as setting up collider objects for physics, limiting the teleport region, setting up lighting, creating trigger areas for everything that is to be interacted with, and of course adding the movable objects separately. So in no way is the mesh model a complete game engine scene, but it still requires quite extensive modifications and additions. And this ties very closely to the applications that are required. So for example, in this picture, you'll see a number of objects that are actually movable in the VR, and then a number of objects that are completely static. This is of course because the indoor mapping system does not know that we want to be able to separate objects, but everything is baked into a single mesh. And to make those objects movable would require extensive manual modeling and separating them from the rest of the mesh. All right, and finally, what are the conclusions that we can reach from these experiments? So thinking about the benefits, we can see that VR can be used for multi-scale visualization. It has very high visualization capabilities and capabilities for interaction and animation. And these begin to turn the application into an experience. Of course, attaining this places high requirements on the data. And of course, traditional multimedia is still usable. So if we have videos, we can bring them into the game engine scene and virtual reality. The major future research needs that we encountered would of course be further automation of game engine scene production. So not only automatically modeling the environment, but also beginning to include the semantics that are required to turn it into a usable game engine scene. We can also say that game engine capabilities are still not very well used in geo-information, especially in VR, and this would of course require further work. And finally, there are the emerging browser-based game engines and VR that would be very interesting for geo-information, especially for the disseminated applications. And last but not least, I'll of course want to acknowledge the entire team behind the work and the publication, so this has not been a solo effort. And of course also acknowledge the funding organizations. So thank you for watching this presentation, and I should be available for questions in the conference session, and otherwise I've included my contact details in this final slide. Thank you.